Okay, my name's Alex, and I'm gonna be doing this for you. Okay, we have to find the hydrogen atom that most readily participates in the chemical reaction with NaOH. It's gonna be the H right there, because you're just losing one of the H's for an H2O. Yep. Alright, next problem. 10.22 grams, 40 grams per molar mass, and 0.5 liters. You convert that from the milliliters, 1,000 milliliters a liter. Molarity is just moles over liters, so just plug in 10.22 times 40 over 0.5. Of course, it's just 10.22 is the grams you have times the molar mass, and you can find the amount of moles. And we have 0.511 molarity. Next question. Yeah, okay. This is going to take a while because I'm doing this on my iPad, but... Okay, next question. Find the pKa of lactic acid. Now, how do we find the pKa from this whatever? So we just need to find the 1/2 EQ point where pH equals pKa, because we know what the pH is. So the equivalence point is 16. So half of that is 8, so it'd be like 3.8, approximating. Look, I recorded this, I solved the problems first while recording it, and then I'm recording the audio later, so this is gonna take a while. So yeah, might as well talk to you in the meantime. But just giving you a heads up for the next question, I totally counted wrong, but you see the C3H6O3, that's the acid, and the Na plus, and that the ions are ionizing, right? So since this is there's more acid than ionized parts, it means it's before the 1/2 equivalence point, so it'd be before 8. Yeah, let's just wait now. I think I was stoned or something. Okay, anytime now, draw an X. Alex, come on. You're taking way too long for this. I mean, it's been 3 minutes already, and I'm just yapping to you. Please don't give me a 0, Mr. Roberti. Look, Mr. Roberti, my Apple Pencil kept dying, so... Yeah, this is why it keeps well, it's not even Apple Pencil, it's just a knockoff. But it kept dying, so I had to yeah, just ignore this counting part. There's actually 4 of the C3H6O3. Yeah, frick that. Okay, there are more acid. Yeah, there's more acid. So more acid to dissolve things, as I explained earlier. So it's before the EQ point. I mean 1/2 EQ point. Okay, chop chop, chop chop, chop chop. Justify your answer, but you kind of already did. Chop chop. Hurry up, man. Why am I taking so long? God. Yeah, from hindsight, this is kind of a bad idea, recording my audio afterward, because now I'm just really impatient, and this video is 20 minutes long. Yo, come on. What are you thinking, bro? Stop thinking so hard. It's not that deep. Okay, in hindsight, this was a bad idea. Hurry up. Dang. Yo, did I just space out? Yo, I'm so sorry, Mr. Roberti. You don't have to. Okay, I'm actually writing. More acid. Man, I explained this to you 3 times already, but yeah. Okay, switch the page, bro. Switch the page. Give me something new to talk about. It's been we spent 2 minutes doing this. It's taking forever. Okay. 5% battery. Okay. Third experiment. Okay, this is just a quantity of heat. They give you all this stuff. So we're going to have to do a Q equals MC delta T equation. We got 100 ml, 0.5 molarity lactic acid. So, yeah. So we have to do the MC delta T. Delta T is 23.2 minus 20. We have the C, and the mass is what am I writing? Oh, I skipped that question. Whoops. Okay. Yeah. So you have to draw the curve, and since it's twice the amount, it's gonna have like the half equivalence point of, it's twice the amount with the same volume of solution. So the half equivalence point of the experiment 1 will be the actual equivalence point of experiment 2, because it's just exactly double. Exactly double. I meant. I don't know. I'm like geeking out right now. Okay. Yeah. Yep. Okay. I explained to you the E already. So yeah, it's a Q equals MC delta T type. Yep. You don't need to underline all that. I'm sure you're reading this yourself, so I'm not gonna read it to you. 1.0 grams per milliliter. We have 200 milliliters total. That's where we get 200 grams from, just so you know. If you're wondering where that came from, quantity of heat, Q equals MC delta T. We have the M, which is 200 grams. Man, why did I write so slow? 200 grams. Yo, write the G. What are you doing? Okay. Times the C, the specific heat capacity, right? So that's 4.2 joules. Why am I not writing it? What are you doing, Alex? Yo, I definitely spaced out. 4.2 joules per gram times degrees Celsius. Okay, now you're actually writing. Okay. And then just times the change in temperature, which is 23.2 minus 20. Excuse me. Yeah, and we get a Q of 2,700 joules. In joules, you don't need to do 2.7 kJ just yet. Okay, next part of this question. Hopefully it's the last, because I think I spent like way too long on this question, because I just kept spacing out. Anyways, okay, calculate the molar enthalpy of the reaction in kilojoule moles reaction and include sign in your answer. Okay, molar enthalpy is the delta H. So we have to find the Q reaction. Oh my god, why did I take so long to write Q reaction? And you also have to find the moles of solute, and we'll do that. It's just I'm taking forever. Yeah, okay. First need Q reaction. Why did I write so take such a long time? Delta H equals QRX equals Q reaction over moles of solute. Oh yeah, this is the point where my pen actually died, so I had to recharge it. So yeah. Yep, that's correct. And now how do we get Q reaction? That's just negative Q solution. And the Q of solution is that, and we make it negative, but we need in kJ, so it's just negative 2.7, as I mentioned before. That over the moles of solute, and we have to calculate the moles of solute. So we have 0.1. Why are you waiting so long? 0.100 liters times the molarity, and that will just cancel out the liters and you get the moles. And then that becomes negative 54 kilojoules per mole. Okay. That's supposed to be a delta H. Looks like an OH. Yep. Okay. Student claims if heat is lost from calorimeter to the surrounding air during the reaction, then the experimental value, blah, 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 justify your answer. Okay. Student claims, I agree. Oh, yeah, okay. I see. Look, if the system loses heat, then like since delta AHQ reaction and mole solute, oh my god, why am I taking so long? It just means lower final temp, which means not delta H, delta T, Q, delta T, which means the Q, and what is it? Why is that a capital T? Okay, delta T. Oh, it is a capital T. Delta T, the Q of the change in Q and the change in it was change in heat. Oh yeah, because Q solution and change in heat. They'll all be what did I write there? They'll all be smaller because they'll all be smaller in actual value. Dang, I can't even read my Apple Pencil handwriting. Okay. Yeah, you got a 1/n concentration graph. And since that's linear, you automatically know it's second order. So that's the answer to A. I mean, I just memorized that, and I think you can just memorize that, so yeah, just do that. Yeah, so I just wrote it down. Okay. Blah, blah, blah. Oh, okay, this is just unit conversion. So, yeah, come on. Unit conversion, you're going to do 6.52 times 10 to the negative 7, and you got NO2. For each mole of NO2, for 2 moles of NO2, you have 1 mole of oxygen, O2. Yeah, I'm still writing, but what you're going to see in a second is I'm going to plug 6.52 times 10 to the negative 7 times 1/2, because for every that you get half for oxygen, and it's just going to be exactly half of this, and you'll see, but just give it a second because I take forever to write. 2 moles NO2, yep. 1 moles of O2, yep. Equals 3.26 times 10 to the negative 7 moles per second. Oh yeah, because of the rate. Yeah, I don't know why I didn't. Okay. Next, question 6 on the 2024. We have to draw the Lewis diagram. You have to know your formal structure, formal charge. So I'm gonna put down. So I'm just gonna draw this real quick, but you'll see why it checks out. So you make sure your bonds are in. I'm just gonna put a double bond because I already know this thing. Why did I take so long? Put in double bonds, and then you put because it's oxygen, which is 6 each, 6 valence electrons each, which gives you 12, plus the 4, which gives you 16. So you got 1, 2, 4, 6, 8, plus the 8. Okay, yeah, we have 16 electrons. Now you have oxygen is 6, as I mentioned before, and the count is 6. So 6 minus 6, 4 minus 4, 6 minus 6. they all equal 0, so the formal charges work. So that's like an actual thing. I wrote I did. I don't know why I did that, but I did the thing. And student says bond angles are different. Yeah, they are, because you see that, yeah, I agree. I'll explain it to you once I write this down, which I was doing in the past. I agree there is no... What did I write? Oh, yeah, okay. There's no longer the non-bonded electron. You see that right there? That is pushing, like, those oxygens down because it's, like, repelling it. So it'll make the angle, like, slightly, more different. And since that's gone because it became bonded, it's just not there anymore to force it. Yeah, pretty straightforward. Question 7. Yeah. Okay. Calculate the mass of solid NaCl that you need to use. Okay, well, we have 0.1 liters. Once again, do your unit conversion. Yeah, I don't know why I wrote it that far out, because you kind of need to do calculations. That's kind of a bad habit of mine. Okay, I crossed that out. So you're going to use 0.1 liters times the 0.34 molarity, which is moles per liter. And we can just do 1 liter because we need this to cancel out. So we need it on the bottom times the 58.4 grams to moles. So those moles cancel out. Those moles will cancel out. The liters cancel out. And now we just have grams, and that gives us what we need. Now we just multiply all the tops, all the bottoms. Excuse me. We divide them, and we get 1.99 grams of NaCl. Excuse me. Okay. Works out. Finally, we just have to do the we just have to fill in this table on how to actually do the thing. So yeah, they give you all the stuff that you don't really need to use. Well, they give you all the stuff and you just have to use it. So we just have to combine the solid sodium chloride with 100 milliliters of distilled water, because that's what they use on the field. Like, you're not allowed to use any other thing because there's like minerals in them which will react with the sodium, which kind of messes up the scientific process. And we're going to use that 100 cc volumetric flask that they provide us, because these AP guys really like it when you use their question. I mean, obviously. But yeah. So now we swirl the mixture. Okay, now we just have to add more. So we fill the volumetric flask with more distilled water to the 100 cc, 100 milliliter calibration mark, which I'm going to write in a second. I spaced out. It's either I spaced out again or my pencil died. I have a knockoff, so yeah. Okay, well, is that the last page? No, it's not. Okay. Yeah, I really thought I was done there. Okay, so we have this NaCl, right? So we have 15 minutes instead of 30 minutes, which means since they start from the same point, they're just going to have less time to travel in general. And even though Y is more nonpolar than X, because if it's more nonpolar, then it will dissolve in the NaCl solution, which means it goes up more, right, to the solvent front. Except for there's less movement for it for both of them, so it doesn't like accelerate up as fast, if I can say that. So the distance in between them will be less. Yeah, so less time, less travel. And ACL is non-polar. Okay, yep. Why did I take so long, man? And I still have a 3-minute video after this of question 7 for the 2025. But yeah, okay, less time, less travel, which means the separation will be smaller. Okay, I'm done. I'll see you in a sec. Okay, this is the question 7 for the 2025 FRQs. This is my last FRQ for this video, and I'm really hoping that I didn't spend too long, but it looks like I spent 3 minutes on this, which should not happen. Okay, which particle except the proton is the O, because it's the COOH tail that is often seen in these compounds. So if you get that O, you're correct. For question B, question 1, once you calculate KB. Now, KB is like the formula for KB is given to you above, as KB equals concentration of C2H3O3 with the times the concentration of OH minus over the concentration of the C2H3OH minus. Once again, my pen died, so just give me a sec. Oh, now it's not. I was trying to write the KB formula, and then I just realized they gave it to us, so yeah, okay, don't need that. Anyways, you're going to use that, but first you need to use a rice table to find that, which I can't really fit on here. But, so here, use a rice table, which is the reaction, then you have the initials and concentrations, and then you finally have that. And you get a KB of 6.8 times 10 to the negative 11 after plugging those concentrations into the KB equation. Now for B part 2, using your answer to part B part 1, calculate the value for Ka. Now Ka times Kb equals Kw, and at 25 degrees centigrade, it's just 1 times 10 to the negative 14. So you can just use that divided by the Kb, which we got earlier, which is 6.8 times 10 to the negative 11, equals the Ka. I'm going to get rid of that equal sign because it's kind of misleading, which is 1.5 times 10 to the negative 4. And then finally for C, a student claims that H3O plus, so hydronium, is a catalyst for the reaction. Now, do you agree or disagree? Now, and justify your answer based on the mechanism given. Now, we see that in step 1, you have H3O plus, but then you don't see it until the end of step 2 as at the end, which means you can cancel it because they're on opposite sides. And in the overall, it's not shown. So I agree, it is a catalyst, as a catalyst is not used in the reaction, which it wasn't. It came out unharmed after being used in the first and coming out produced in the second, which means it's canceled out. And yeah, it's not an intermediate or anything, and it doesn't really appear in the overall reaction mechanism. So yeah, I agree. Okay, thanks.